The birthplace of a tornado. The formation of a tornado begins high above the ground, in towering thunderstorms known as supercells. A supercell is not an ordinary storm. It is a self-sustaining engine with its own rotating core called a mesocyclone. These storms are rare but incredibly powerful, capable of producing the world's most violent tornadoes. For a supercell to form, three ingredients must collide. The first is moisture, warm, humid air rising from the surface. The second is instability. When warm air near the ground meets cold, dry air higher up, it creates a situation where the lower air wants to surge upward. The third is wind shear, a change in wind direction and speed with altitude. Together, these factors create a rotating column of air within the storm. Picture the lower atmosphere as a series of invisible spinning tubes. When an updraft from a developing thunderstorm tilts one of those tubes upright, the rotation stands on end, forming a vertical column of spinning air. This is the foundation of a mesocyclone, and it's the first step toward the birth of a tornado. The mesocyclone takes shape. As the thunderstorm strengthens, the mesocyclone tightens. Rising warm air and falling cool air start to twist around one another. Inside the cloud, raindrops are being tossed in circular paths. Lightning flashes through anvil-shaped clouds as pressure drops. From the ground, all of this is invisible, just another darkening sky. But inside, a war between temperature and motion is intensifying. Meteorologists track this invisible rotation with Doppler radar. When a storm begins to rotate strongly enough, radar displays a telltale hook echo, a shape that curls around like a claw. It's the meteorological fingerprint of potential disaster. At this point, the storm has enough rotation and structure to produce a tornado at any moment. The downdrafts and the dance of air. What happens next surprised scientists for decades. They once believed tornadoes formed simply by spinning faster until they touched the ground. But new research revealed the crucial role of descending air currents known as downdrafts. In a supercell, two main downdrafts exist: the forward flank and the rear flank. The forward flank downdraft forms as rain-cooled air is pushed out ahead of the storm, while the rear flank downdraft forms from drier air descending around the backside of the rotation. When this rear downdraft slams into the ground, it spreads out in all directions. As it curls around the mesocyclone, it creates a zone where warm, moist inflow from the ground collides violently with cold, dry air from above. This collision accelerates the rotation. It's as if the atmosphere has found a way to twist the air tighter and faster. Near the surface, the spin becomes concentrated, forming the embryo of what will soon become a tornado. The funnel emerges. As the spinning air column tightens, pressure inside it drops sharply. When air pressure falls, moisture in the air condenses. This is why a tornado becomes visible. Not because of dust or debris at first, but because of the condensation cloud forming inside the rotation. The funnel you see reaching down from the clouds is only the visible outline of the tornado's core. The true tornado is a column of invisible wind moving faster than the eye can follow. Sometimes that funnel never touches the ground, but when it does, the rotation picks up dirt and debris, making the tornado appear darker and more defined. At the moment the funnel connects the storm cloud to the earth, a full tornado has been born. The air at its center can be moving at more than 300 miles per hour. With pressure so low, it can make buildings explode outward. It is, for a few terrifying minutes, the most violent weather phenomenon on the planet. The mature tornado. Once formed, a tornado behaves like a living creature. It feeds on the storm's warm inflow and the energy of the updraft. As long as that balance holds, it can sustain itself, growing stronger, wider, and more organized. Inside the tornado, chaos rules. The outer walls spin in a violent dance, while the core remains calm, much like the eye of a hurricane. Around the main funnel, smaller suction vortices may form, spiraling within the larger vortex like planets orbiting a star. These mini tornadoes cause the bizarre damage patterns often seen after a storm. One house untouched, the next obliterated. When you stand miles away and watch a tornado cross the horizon, you are seeing a perfect balance of power and physics. The rising updraft keeps it alive, the descending downdraft shapes its motion, and the inflow at the surface fuels it with warmth. The tornado moves as the storm moves, sometimes straight, sometimes turning unpredictably. It can last seconds or more than an hour, depending on how long the parent storm remains stable. The roping out and death of a tornado. Every tornado eventually weakens. As the storm begins to lose energy or shift its structure, the inflow of warm air is cut off. Without that fuel, the vortex stretches and thins, becoming a narrow rope dangling from the clouds. The once mighty funnel starts to twist and curve erratically before finally dissipating. Even as it fades, a dying tornado remains dangerous. Winds can still exceed hurricane strength, and new circulations may form nearby. Some supercells produce tornado families, multiple funnels forming one after another along the same storm path. What's left behind is a trail of destruction. Trees shredded, homes flattened, soil stripped bare. But from a meteorological perspective, that destruction is data. Every broken object tells scientists something about wind speeds, pressure changes, and the inner workings of these storms. Measuring the power. After the sky clears, experts use the enhanced Fujita scale to rate the tornado's strength. This system measures damage to estimate wind speeds, from EF0 for light damage to EF5 for near total devastation. An EF0 may tear shingles from roofs and uproot small trees. EF3 tornadoes can destroy well-built homes. EF5 tornadoes are almost beyond comprehension. Entire neighborhoods swept clean, steel beams twisted, asphalt peeled from roads. The difference between an EF1 and an EF5 is not just strength, but energy. The most powerful tornadoes contain hundreds of times more kinetic energy than weaker ones. They are the atmospheric equivalent of nuclear explosions in terms of raw force. Yet they arise naturally, without warning, from the chaotic interactions of air and moisture. Tornadoes beyond Tornado Alley. While the United States experiences more tornadoes than any other country, these storms occur almost everywhere on Earth. In Bangladesh, tornadoes strike during the spring monsoon season, sometimes killing hundreds in densely populated villages. Argentina and southern Brazil experience violent storms in their own tornado corridor. Even Europe and Australia see smaller but still dangerous tornadoes each year. The reason the US produces the most extreme tornadoes lies in geography. The Great Plains create the perfect meeting ground for cold Canadian air and warm Gulf moisture. With few mountains to block their interaction, the atmosphere becomes a mixing bowl of instability, leading to the dramatic weather patterns that define Tornado Alley. Technology and discovery. Modern meteorology has transformed our understanding of tornadoes. Doppler radar can now detect the rotation of storms before a funnel even forms. Dual polarization radar can identify debris being lifted into the air, confirming that a tornado is on the ground. Storm chasers and researchers use mobile radars and drones to collect data from terrifyingly close range. These instruments record wind speeds, air pressure, and temperature changes within the storm. Every new tornado provides information that refines forecasting models and helps save lives in future outbreaks. Despite these advances, tornadoes remain notoriously unpredictable. Scientists can forecast the likelihood of tornadoes forming hours in advance, but pinpointing exactly when and where a specific tornado will touch down is still beyond our reach.